How do you say that, okay, some number of operations are required for very basic? How many operations are required? For searching a name in the list of, say, 10 million students. Can you think of this? No? Suppose I want to search. Suppose okay, how many students are there in this institute? Say 3,000. Am I right? How much? 1,000. Okay, let us take 1,000 students. Okay, in the set of, suppose you have a list of 1,000 students and you want to search a name of one student in that list of 1,000 students. Okay, how much? Means what will be your algorithm? What will be your method of computation? Right? What will you do? If it is sorted, then you have what is called a binary search. Am I right? If it is sorted, then you have binary search, and binary search, if there are n students or n elements in the list, they are arranged in a order, you will apply binary search and it requires order logging operations. What is important is operation. What Alan Turing did is Alan Turing gave us a formal model of computation based on which it is not really required to define precisely, okay, what an operation means. Okay, that operation is expressed in terms of the number of steps which are required for the complete computation. The result of the whole computation is precisely defined. Okay, so non-determinism is somewhere in between, and that helps us to specify. That helps us to have a shorter description for the specification. This shorter description for the specification also translates to this fact that if you have a non-deterministic description of an algorithm, you require less number of steps. Right? That is an intuitive idea. The big problem here is, suppose I have a non-deterministic algorithm or some problem. Now let me give you one of the practical problems or one of the important problems. Have you heard about traveling salesman problem? Traveling salesman problem. You have, say, nowadays we can talk about the whole world, or you can say cities in India itself. Suppose we take some 40-50 cities within India, right? So 50 cities in India, they are connected by, say, railway network, okay? But traveling salesman is given a job of visiting all these 50 cities in such a way that, okay, he has to travel by railway, right? Whatever connections are available, and you know that in India the railway network is quite extensive. He has to travel in such a way that the total amount of time required for visiting all these cities is less. So he is optimizing time. Instead of optimizing time, you might like to optimize the distance traveled. Yet another optimization possible could be the amount of cost. However, the restriction is he has to visit all the 50 cities. If I'm very sure that we have studied an algorithm for this problem. Am I right? No? In the course on, you have a course on algorithm, design of algorithms. You have a course on data structures. Right? So, after the course of data structures, or in the later part of the data structure, you will be studying about the algorithms. And there are algorithms. In the algorithms, you will study about what is called backtracking. You study about, have you studied that? Do you know the term called backtracking? There is a term called branch and bound. So please note that what I am talking about is an extension of this. Backtracking, branch and bound are very important techniques in artificial intelligence. Right? You know, in artificial intelligence, when we want to give this intelligence to the computers, okay, these are the traditional techniques, okay, which are already very useful. Now, you can apply this for their traveling salesman problem because we want to find out the minimum cost tool, but the tool is not like a shortest path. Have you heard about the shortest path problem? Yes. That is the Dijkstra's shortest path problem. You must have heard about Dijkstra's algorithm. There is another algorithm called Floyd-Warshall's algorithm, but that is not for finding out the shortest path from a source to a destination, but from all pairs. Right? So, the Dijkstra's shortest path problem does not guarantee you to visit that the salesman visits all the cities. If that additional restriction is put there, then the problem becomes a non-deterministic polynomial problem. And it is possible to write a very simple non-deterministic polynomial problem for this particular thing. Now, what Stephen Cook did is Stephen Cook used Alan Turing's model to actually prove that if I have a polynomial algorithm for some simple problem, and the problem is a satisfiability problem, in particular a restricted version of satisfiability called 3-SAT, if I have a deterministic polynomial algorithm for 3-SAT, then I have a deterministic polynomial algorithm for all NP-complete problems. Right? I suppose you have not studied this aspect, did it? Or you have studied this? Okay, maybe I think they have. You are in which year of engineering? Third year. How many of you are in the computer engineering? Computer engineering, quite a few of you. Okay, so in fact you will need to study this. Okay, as a part of your BE curriculum or MCA, MSc curriculum as well. Okay, so please note that. Okay, what was believed till now is this that well accepted conjecture is P not equal to NP, where P stands for the set of all problems for which we have a deterministic polynomial algorithm, and NP stands for the set of all problems for which we have a non-deterministic polynomial algorithm.